Imagine being able to predict and prepare for the intense storms that rage across our solar system, threatening the very spacecraft that keep us connected to the cosmos. A groundbreaking discovery by the European Space Agency's Solar Orbiter mission has brought us one step closer to achieving this goal. By tracing the origins of super-fast electrons back to the Sun itself. But here's where it gets fascinating. These electrons, known as Solar Energetic Electrons, SEEs, can travel at nearly the speed of light and pose a significant threat to spacecraft and astronauts alike. The findings of this research will enable scientists to make more accurate space weather forecasts, protecting our valuable spacecraft and keeping them operational. As Daniel Muller, an ESA project scientist for Solar Orbiter, notes, knowledge such as this from Solar Orbiter will help protect other spacecraft in the future by letting us better understand the energetic particles from the Sun that threaten our astronauts and satellites. So, how do these electrons get accelerated to such incredible speeds? It all starts with the Sun, which can accelerate electrons to nearly the speed of light before launching them into space. There are two types of SEEs, each with its own unique characteristics. The first type is created during intense solar flares, which are bursts of high-energy radiation from the Sun's surface. The second type comes from coronal mass ejections, CMEs, larger explosions of hot plasma and magnetic fields from the Sun's atmosphere. CMEs tend to be higher energy events, carrying higher energy particles that can damage spacecraft, making it crucial to understand how these particles travel. According to Alexander Warmoth, lead author of the study, we see a clear split between impulsive particle events, where these energetic electrons speed off the Sun's surface in bursts via solar flares, and gradual ones associated with more extended CMEs, which release a broader swell of particles over longer periods of time. While scientists previously knew that there were two types of SEEs, this research has revealed more in-depth information about how solar events form and fling them off the Sun. The Solar Orbiter, launched in 2020 as a joint mission between the ESA and NASA, has been instrumental in observing hundreds of events at different distances from the Sun, using multiple instruments to gather data. As Warmoth notes, we were only able to identify and understand these two groups by observing hundreds of events at different distances from the Sun with multiple instruments, something that only Solar Orbiter can do. During its first 5 years in space, the Solar Orbiter has observed a wealth of solar energetic electron events, allowing scientists to perform detailed analyses and assemble a unique database for the worldwide community to explore. The Solar Orbiter's close proximity to the Sun, coming as close as 42 million kilometers from the surface, has enabled it to measure particles in a pristine early state, accurately determining the time and place they started at the Sun. One of the unanswered questions that this research addressed was why there always seems to be a lag between when researchers spot a flare or CME and the eventual release of electrons. Previous observations have noted that the electron release can take hours, but it turns out that this lag is at least partly related to how the electrons travel through space. As Laura Rodriguez-Garcia, ESA Research Fellow and co-author of the study, explains, the electrons encounter turbulence, get scattered in different directions, and so on, so we don't spot them immediately. These effects build up as you move further from the Sun. The space between the Sun and the Earth is not empty, but filled with charged particles that constantly stream from the Sun, pulling its magnetic field along for the ride in a solar wind. This solar wind can disrupt how seas move, making it essential to understand its effects. The ESA plans to launch the SMILE mission next year to continue measuring solar winds and providing even more details on how energetic electrons interact with the Sun's magnetic field. As Mueller notes, thanks to Solar Orbiter, we're getting to know our star better than ever. This research is a testament to the power of collaboration, made possible by the combined expertise and teamwork of European scientists, instrument teams from across ESA member states, and colleagues from the U.S. But here's the question. How will this new knowledge impact our ability to predict and prepare for space weather events? Will it enable us to develop more effective protective measures for our spacecraft and astronauts? We'd love to hear your thoughts. Do you think this research will revolutionize our understanding of space weather? Or are there still more questions to be answered? Share your opinions in the comments below.